So, good morning or good afternoon to everyone. I'm pleased to introduce you my presentation entitled Using SIMBA for Low Voltage Network Protection Study in Nuclear Installation. My name is Guillaume Batz, and I'm working as electrical system expert within the company Technicator. My agenda will be quite classical. I will start by a brief introduction of the company and of the problem we have with low voltage network. Then I will explain how to model a low voltage network using SIMBA. I will share with you some simulation and results and end by a short conclusion. So, as a small and brief introduction, Technicatum is a French leading company in the field of small nuclear reactor. We are known for our historical activity of naval propulsion, but we are also involved in energy production, like the small nuclear reactors, also research and medical reactors, and we just started a new spin-off for industrial hot water. I will not detail what is a nuclear installation. It will be too long, but just as a summary, in the field of nuclear reactors in general, the nuclear safety is a priority above all. The safety in a nuclear reactor is ensured by several means. Of course, it starts by a good conception and good operation of the plant, but we also use several safety equipment like valves, pumps, or actuators to ensure the safety. A significant number of the safety equipment are supplied by a low voltage network. Typically, in Western countries, we tend to use a 24-volt DC. It's a safety we supply this ensured also by batteries. And the reliability of this DC network must be as high as possible to ensure the availability of all the safety equipment. However, despite the highest quality we can bring into the design of the fabrication, we have to take into account that an electrical fault may still happen in the network. So for every possible kind of failure, mostly short circuit, must be detected and cleared without causing damage to other equipment. For confidentiality reasons, all the value examples of this presentation are intentionally modified, so there is no problem to share those data with you. I just would like to make you realize how many numbers of study cases there is when it comes to low voltage study. First, we have to take into account the power supplies. We can have from 1 to 3 DC battery loaders connected. We can have 1 or 0 batteries when we are in maintenance. We also have several operating conditions. Battery can be in charge, can be floating, can be in partial discharge or fully discharged. And the network has also a lot of different configuration. In a nuclear plant network, we can have up to 15 distribution switchboard, up to 40 loads by switchboard. We have lengths between 1 meter to 100 meters from the source to the final load, and also several kind of short circuit. Can be a full short circuit, can be independent short circuit, partial short circuit. So we have more than 10,000 study cases by network. We have 4 networks for each reactor. So it's quite, as you can imagine, it's quite complex. And in the past, before SIMBA, we had to identify the worst case scenario by sampling several simulation scenarios. Of course, it was not possible to launch and perform all the calculation. So the identification of the worst case scenario is always long, complex, very time consuming, and there's always a risk of wrong identification. But now with SIMBA, we have like a game changer in low voltage network study, because through the Python interface, we can decide to perform every single study case and then make it identify the worst scenario. So now we can bring the comprehensiveness of all the study case, and we sure that we identify the worst condition and check that everything is okay. So now a few words of how to model a low voltage network. The protection of low voltage DC network is mainly ensured by DC fuses, and fuses are really the key parameters for protection. For each short circuit, it must be checked that at least one fuse melts and clears the short circuit current. And of course, when possible, only one fuse trips to maximize the availability of the equipment. But in low voltage DC network, we have a special difficulty that we must check that the opening surge voltage does not cause damage to other equipment. Indeed, we can reach up to several hundred volts of over voltage. It is way above the standard rated voltage of the equipment. So the modeling of the DC fuses is critical to simulate correctly the pre-fusion time, the arcing time, and the over voltage. It looks like a very difficult work, but in fact, DC fuses can be quite accurately modeled using simple RC circuit. And I would like to quote here the great study of NTT, who's called Modeling of Fuses for DC Power Supply Systems, including RC time analysis. Very good quality work. And you can see on your left what a short circuit looks like with in a very small amount of time, great surge of great rise of the current, in that case up to 1,500 amps. Then the fusing, the arcing time, the fusing of the fuse, which introduce quite high voltage. In that case, it's 300 volt voltage in a 50 volt network. So using RC modeling, we just have three parameters to identify: fusing energy in joule, the equivalent resistance, and the equivalent capacitance of the RC model. So in order to make an accurate modeling, the first step was to build a short circuit generator, and we achieved it using 650 farad supercapacitors. With the right series and parallel connection of supercapacitor, we can lead to 24 volts, 5 kiloamps short circuit capability. Here on your left, you can see in that box we can insert the fuse that we want to test and perform the test and measure all the results. Then the fuse can be modeled with SIMBA. As you can see, it's quite simple. We have mainly two branches: one pre-arcing branch where the fuse acts just like a small resistors, and then the arcing branch where the fuse like RC circuits. The transition between the two branches is depending on the arcing time and the fusion energy. Here we have some results. You can see in blue measurements with a Rogowski sensor, and in red the curve generated by SIMBA. As you can see, even with a simple RC model, we can match the reality. We are especially good in voltage spike and current spike. And of course, maybe in modeling we have a little bit smoother, but it's very good results, a very good approach for such a transient phenomenon. Of course, the other parts of the L-bit network are also modeled in SIMBA: the loaders, the battery, cables, loads. Here you can, for example, see an example of one converter input filter with differential or zero sequence capacitors, diode, and inductance, for example. Now I would like to present you the strategy to run the simulation. I present you here a small extract of the model. Here is only a small part of the model, less than 1/4 of the total model. But you can see the DC power supply, the battery, the fuses, the switchboard, cables, and the outgoings to the loads. The cable plays an important role in short circuit study. They are represented by a RL circuit in SIMBA. And at each node of the circuit, there is a potential location of short circuit. So once a model is built on SIMBA, we use a Python interface to set up a network configuration and run a short circuit calculation at each node of the circuit. For instance, a single execution of the script represents about 115 simulation cases to be performed. For each study case, SIMBA Python library is used to create the short circuit, run the simulation, retrieve the results, mainly from the voltage probes. And for each study case, the Python interface itself checked that the proactive coordination rules are respected, and checked also that over voltage are below the acceptable thresholds of the components. Then once it is done, we clear the short circuit, we reset the fuse for the next iteration. We also use multiprocessing in order to run several processes at the same time. And we had good results. The execution time is roughly divided by a factor 2. And then we reshape all the results and export them to CSV or Excel files, right, using Pandas module. Here is a small summary of the simulation process. And we start for the Python interface, the multiprocessing, and you can see here the 2 loops for each of the 10,000 configuration. We play the simulation of a short circuit calculation at each node. Then we iterate for each node, filling the result file at every step. Once the configuration is finished, then we move to the second configuration and so on. And we can do that with up to 4 parallel process. So we'll jump quickly to the conclusion to respect the timing. As a conclusion, from our point of view, SIMBA is not only a power electronic software, it can also be used for electrical network study. And in general, it can be used every time that a large number of simulation is required. The Python interface makes it possible to perform all the possible simulation cases, which ensures the comprehensiveness of the study. And to our knowledge, it's the first time that we can that there is a tool that allows us to do that. SIMBA can calculate and provide results for protective coordination study and also transient and lower voltage simulation. It's also a game changer because in the past we used to use one dedicated network software for the protective coordination study and a transient software like SIMBA for the detailed and transient simulation. Now we can have one single tool to perform both, and I think it will save us a lot of time, and very important to us and for all the application where where safety is very important, and where we don't like to depend on a human to get the right results. The worst case scenario can be identified automatically, because with Python interface we can perform all the study cases, and he does not need us to identify the worst case. He does it automatically. So we have a great confidence in the final results. I finished yet. Thank you for your attention.